Now we'll study about isochoric or isometric process. So say if a gas is given in an initial state P1, V1, T1, and say if the gaseous state is changed to final state by a thermodynamic process where we can say its volume remains constant. So we can say the pressure will be changed to V2, volume remains V1, and temperature correspondingly will change to T2. And if volume is constant, we can write delta V is 0, as well as at every instant volume is constant, we can write dV is also equal to 0. And for initial and final state using mole conservation or by ideal gas law, we can relate that P1 by T1 is equals to P2 by T2 as volume is constant. So for relating the thermodynamic coordinates of the two states of gas between initial and final, you can use this relation. And by first law of thermodynamics also we can state we have dq is equals to du plus dw. But here we can state dw is equal to 0 as volume is constant. If volume is constant, neither compression or expansion takes place. So work done by gas will be 0. So the term of work will vanish. So here dq is equals to du, which can be written as ncv dt, as internal energy is ncvt. So we can simply write total heat supplied, which is used in raising the temperature of gas or used in increasing internal energy. This q can be written as integration of dq, which is integration of ncv dt from rising temperature from T1 to T2. So here heat supplied can be directly written as ncv T2 minus T1, or the value of Cv we can write in terms of gas constant as nR by gamma minus 1 into T2 minus T1. So be careful about these relations. These are quite useful for calculation of heat supplied in isochoric process and various numerical problems. Now, as discussed, we can directly write all thermodynamic parameters for an isochoric process. As we have discussed, the heat supplied is nR by gamma minus 1 T2 minus T1. If we find out the internal energy change as it is equal to the heat supplied, because work done here is equal to 0, so this can also be written as nR by gamma minus 1 T2 minus T1. So these are the three thermodynamic parameters involved with isochoric process. If we just analyze ID for an isochoric process, that also you should understand very carefully, because there are many applications of ID for an isochoric process. As their volume is constant throughout the process, we can state that a simple ID curve can be plotted for an isochoric process, which is a vertical straight line. It may either go up or come down. If initial state to final state pressure is increasing, this will go up, and if pressure is decreasing, the volume remains constant here. So if pressure is decreasing, it will come down. You can see from initial to final state here, delta V is 0 as well as dV is also 0. But several times it happens that in a given process, delta V is 0 but dV is non-zero, like if we talk about some non-isochoric processes. So these are like if an ID curve is plotted in this manner, say volume is V1 and initial state is S1, final state is S2. And in this situation, the curve is going like this. So you can see the pressure is changing from P1 to P2. Curve is moving like this, such that initial and final state is having the same volume. So we can write here delta V is 0. but in between you can see the volume is changing, so we can write dV is non-zero. So your work done will be non-zero. If we just talk about whether it is positive or negative, so we can see starting from S1 initially up to this point, if this is the intermediate volume V prime, so from V1 to V prime the volume is decreasing or gas is being compressed. So from this point to this point is the total area of the curve, which is the work done on gas. And again from V prime to S2 it is expanded and the area is less, which is work done by the gas. So total work done will be this area, which is the difference of two, and its magnitude can be written as work done is negative because total work done on the gas is more than the work done by the gas in moving from S1 to S2. Similarly, we might have such a situation in which for the given case, the gaseous state is changed from S1 to S2 like this. Initial state is here, final is here. The gaseous state is changing in this manner that initial pressure is less and final pressure is more. The volume is kept at constant at value V1. So here you can state in this situation also first the volume is expanded and then it is compressed, and the expansion volume is you can say here it is more, and when it is compressed again the volume is decreased to the value V1. So we can state the work done in expansion, that is work done by gas is less and work done on gas is more. So again this is the work done, and again we can say work done will be negative here. And in this situation delta V is 0, however dV is non-zero. Similarly, we can plot various processes in which the expansion volume or corresponding to work done in expansion is more. In those cases work done will be positive. In these two cases you can see work done is negative. Similar to the case, we just take up another example. If for a given thermodynamic process PV curve is given like this, in which the volume is kept constant again and the pressure is changed from P1 to P2. Initial state is this, final is this. So here you can see from initial state to another intermediate state V dash, the gas is compressed. So work done on gas would be this, and when the gas is expanded to state S2 and the initial volume, the work done by gas, which is for the expansion, is more. Here again we can see delta V is 0, dV is non-zero because it is changing in between, and your work done will be positive and it is equal to the area enclosed by the curve, and not exactly the area between curve and volume axis, because from this point to this point total area is work done by gas, and from this point to this point the total area is work done on gas. So we'll subtract the two and this area will give us the total work done by gas, so it is written positive.